Pop quiz. What causes the voltage in the coil to appear? A. The magnet is strong. B. The coil has many turns. C. The magnetic flux through the coil is changing. D. The wire is copper. Lock in your answer. We will reveal it in a moment. In this video, you'll learn Faraday's law of induction, what magnetic flux really means, how to predict the size and direction of an induced current, and how this shows up in real devices. Here's the big idea. A voltage or EMF appears only when magnetic flux through a loop changes. Magnetic flux is how much magnetic field passes through a loop's area. It depends on three things: field strength, loop area, and angle between the field and the loop's normal. Faraday's law puts that into a rule. The induced EMF equals the number of turns times the rate of change of flux. More turns, or faster flux changes, make a bigger voltage. No change in flux means no induced EMF. But direction matters too. Lenz's law says the induced current acts to oppose the change in flux. If the magnet's field into the page is increasing, the coil makes a field out of the page to oppose that increase. Let's calculate an actual EMF. We have a 150-turn coil with a radius of 4 centimeters. It sits with its plane perpendicular to the field. The field decreases from 0.3 Tesla to 0.1 Tesla in half a second. The area is pi times the radius squared, so pi times 0.04 squared. Because the field is perpendicular to the loop, the angle is 0 degrees and cosine is 1. The change in flux per turn is area times the change in field, which is area times negative 0.2 Tesla. Divide by 0.5 seconds and multiply by the number of turns. You should get an EMF of about 0.3 volts in magnitude. The sign is set by Lenz's law. Now, let's go back to our quiz. The answer is C. It is the change in magnetic flux that creates the voltage, not just a strong magnet, not a special wire. Here's a common trap. It's not just the magnetic field that matters. Flux also depends on area and angle. You can induce EMF by changing any one of them, move the magnet, stretch the loop, or rotate the loop. So far, we have defined magnetic flux, stated Faraday's law for size, and used Lenz's law for direction. Keep those three in mind as we level up. Ready to lock it in? Tap the link for study guides and flashcards on this topic, so you can keep learning without missing a beat. Now, let's apply the idea to a rotating loop in a uniform field, like a simple generator. As the loop turns, the angle changes steadily, so flux changes smoothly. The result is a sinusoidal EMF. The voltage is largest when flux changes fastest. This time, let's try one where only the angle changes. A 50-turn rectangular loop with area 0.010 square meters sits in a constant 0.4 Tesla field. It rotates from 0 degrees to 90 degrees in 0.2 seconds. Flux goes from maximum to 0. The change in flux per turn is area times field. Divide by the time and multiply by the turns to get an EMF of about 1.0 volts. Direction still follows Lenz's law. To build intuition, remember this. If flux is truly constant, there is no induced EMF. But if you change the area of the loop or the angle, you do get an EMF, even with a steady field. Use the right-hand rule and Lenz's law to decide the direction. Here is a reliable problem-solving recipe. First, identify what is changing: field, area, angle, or all three. Second, compute the change in flux per turn. Third, multiply by the number of turns and divide by the time to get the magnitude of the EMF. To recap, Faraday's law links changing magnetic flux to induced voltage. Flux depends on field, area, and angle, so changing any of them can create an EMF. Lenz's law gives the direction. The induced current always opposes the change in flux. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.